In this video, I'm going to go over just question 21 and 22. So I've got a video go through these 20 multiple choice questions. So let me move question 21. And these are what IB calls paper 2 questions. 21 says, in aqueous solution, potassium hydroxide and hydrochloric acid react as follows. So you can see it's a 1-to-1 equation between reactants and products. The data below is from an experiment to determine the enthalpy change of this reaction. And with this data, we see that there's equal volume and equal concentration for both reactant and product. So this means we have same moles of each one. And since there's one H and one OH on each of these, it's going to be a 1-to-1 neutralization. So we have the same molar amount, which essentially is telling us that our limiting reactant is going to be both reactants. That if this is a perfect reaction and everything reacted, all the KOH and all the HCl would be consumed. So A, state with the reason whether the reaction is exothermic or endothermic. Well, just from the data alone, you can see the temperature increased, which means it's exothermic. Or if you realize it's neutralization and that neutralization is always exothermic, that would be fine too. B, explain why the solutions were mixed rapidly. They weren't looking for you to say for a faster reaction. They're looking for you to realize you're trying to decrease the time for heat loss to occur. The quicker the heat is released, the less time it has to be lost to the surroundings. So that was the point of it. C, calculate the enthalpy change of this reaction in kilojoules per mole. And again, everything's 1-to-1, so your answer would be kilojoules per mole. Assume the specific heat capacity of the solution is the same as that of water. And we're also assuming the density of the solution is the same as water. So a couple common mistakes were that people didn't add the 250 centimeter cube samples together to get a total of 100. So you need to use 100, not just 50, because you're adding both together. 4.18 is your C value, and then 3.5 the temperature change. So 1,463 joules, or 1.463 kilojoules, but that's not kilojoules per mole yet. Okay, you have to find out how many moles you added. You didn't add 1 mole of each of these. You added 50 centimeters cubed, or 0.05 liters, at a strength of 0.5 moles per liter. So if you do the multiplication, that's only 0.025 moles. So before this is kilojoules per mole, first of all, again, I have to confirm that I don't have a limiting reactant, and neither or both are limiting reactants, so 0.025 moles from either one. So now when I divide my 1.463 by the 0.025, this becomes negative 58.52 kilojoules. And then D, identify the major source of air in the experimental procedure. Some of you said the glass beaker, you actually cited the source of the air, but what they're looking for is that the heat loss to the surroundings is the major source of air. And it was caused by the glass beaker. And so then obvious ways to minimize it would be to use an insulated vessel, put a lid on it, graph your results, and extrapolate what the maximum temperature might have been. Those were all valid improvements. And E, the experiment was repeated, but with an HCl concentration of 0.510 moles instead of 0.50. State and explain what the temperature change would be. And this is kind of a tricky question, because what they're getting at is that if KOH and HCl were both the limiting reactant initially, increasing the concentration of just one is not going to change it. It might speed the reaction up because you got some excess HCl there, increasing the number of collisions. But the KOH is still going to limit the reaction, so the overall temperature change will still be the same, whether it happens more quickly or not. And number 22, calculate the enthalpy change for the reaction C plus 2H2O plus a half O2 equals CH3OH, something called methanol. So using Hess's law, I see the CH3OH is in the correct amount, but on the wrong side, so I'm going to flip that over. The C plus O2 plus CO2 gives me the carbon is my reactant that I want. It's the correct amount on the correct side. And then the H2 plus half O2, again, the H2 is the reactant. It's on the correct side, but I do need to double that. So I actually showed you my 3 equations after I flipped the first one, left the second one, and then doubled the third one. And then along the right side, you can see the changes. I flipped the negative 676 to positive, left the negative 394, and doubled the negative 242. And I came up with an enthalpy change of negative 202 kilojoules.